In this problem, we have an air conditioning system, and we have air and R134A, or refrigerant, exchanging heat between each other. So you have warmer air, which is going to be 32 degrees Celsius at the inlet number 1, and it's going to exit as a cooler air at 22 degrees Celsius. Now, conversely, you're going to have colder R134A, and when it exits, it's going to be hotter at exit 4 versus inlet 1, or inlet 3. We can ignore the heat transfer from this entire system with the surroundings. So if we draw our system boundary, it'll be something like this, which would be around the entire system. Make sure you get every inlet and every exit. And we're going to say that the heat transfer from the conditioner to the surroundings, so Q dot, is going to be equal to 0. Also, we can assume that the kinetic energy and the potential energy are equal, and they're both equal to 0. So what we're asked to find here is the mass flow rate of the refrigerant in kilograms per minute. I'm going to call that m dot r for refrigerant, and we're looking for the heat transfer, or the rate of heat transfer, which is going to be on a per unit time basis, which is kilojoules per minute. So we're going to have to find the heat transfer, and it's going to be some number in kilojoules per minute. And this heat transfer is going to be between the refrigerant and the air. So I'm just going to add subscript R here for the refrigerant. So the first thing I'm going to do is apply the energy balance equation over this entire system. So we have 2 inlets and 2 exits, one for each, the air and the refrigerant. So we're going to have our energy balance equation 0 equals the heat transfer minus the power, and this is of the system, not of the refrigerant or the air. This is of the entire system, so it's separate from what we're trying to find for part B of this problem. And now we can add our incoming mass flow rates times our enthalpies. So in this instance, we'll have 2 different mass flow rates. So we'll have inlet 1 and 2 will share m dot A, and inlet 3 and 4 are going to share m dot R. And the reason why they're going to be shared is because the air is a single inlet, single exit control volume on its own, and the refrigerant is also a single inlet and single exit. These two compounds aren't actually going to mix. You're not going to have a mixture between refrigerant and air. They are sealed from each other, so their mass flow rates do stay independent of each other. So I'm going to add the mass flow rate. We'll say A, m dot A, times, and then we're going to say H1 minus H2. And that's just the inlet minus the exit of the air. And then we're going to add the mass flow rate of the refrigerant, m dot R, and that is going to be H3, because that's inlet number 3 minus exit number 4. And again, we don't have to do our velocity or our gravity and difference in elevation, because we were told that kinetic and potential energy can both be neglected. Now, if we move a step further with this equation here, we're also told to ignore heat transfer. So therefore, we have no heat transfer. And then if you look at this device here, it's just an air conditioning system, it's more or less just a heat exchanger, right? So you have no shaft that's going to either emit or accept power. So it's not a compressor, it's not a turbine, it's not a pump. So we can neglect our power as well. And recall that the whole purpose of why I'm doing this energy balance is actually to find the mass flow rate of the refrigerant. So we're looking for this unit right over here. So what I'm going to do is I'm going to rearrange this expression for m dot R. And when you do, you'll have that m dot R equals the mass flow rate of the air times the difference of H2 minus H1, notice the swap there, divided by H3 minus H4. So now to find m dot R, we need a few things. We need m dot A as well as the 4 enthalpies at each inlet and exit. So the first thing I'm going to do is use the ideal gas law. So we'll have that P1 V1 equals mRT1. And the reason I'm using the subscript 1 here is because we were given the volumetric flow rate at 1. So we have 50 cubic meters per minute. So I'm going to convert this into volumetric flow rate because we're also looking for the mass flow rate, and it'd be the mass flow rate of the air in this case. And so yeah, that's why I use subscript 1, because we were given the pressure, the temperature, and the volumetric flow rate at 1, which makes it possible to find the mass flow rate. So now I'm going to rearrange for the mass flow rate for the air. And we're going to simply have that the mass flow rate of the air equals the pressure times the volumetric flow rate divided by the gas constant and multiplying the gas constant by the temperature, all at inlet 1. And now we can plug in our numbers here. So for the pressure, we have 1 bar at inlet 1, but we're going to be using kilopascals in this instance because we're going to want our unit to be in kilograms per minute when it's all said and done. So 1 bar is going to be equal to 100 kilopascals. And the volumetric flow rate was simply given as 50 cubic meters per minute. And we're going to divide that by the gas constant. So to find our gas constant R, we can just use the formula of gas constant equals universal gas constant divided by molar mass. So in this case, it would be the molar mass of air, which would be equal to 8.314 divided by the molar mass, which is 28.97 for air, and it'll yield you with 0.287, and the unit for that is going to be kilojoules per kilogram Kelvin. Finally, we can multiply by T1, which was given as 305 Kelvin. And now if you plug this into your calculator, you'll find that m dot A, so the mass flow rate of the air, equals 57.12, and the unit here is kilograms per minute. So now I'm going to start filling it into our equation for the mass flow rate of the refrigerant. So we'll have the m dot A was 5712, so 57.12, and that's kilograms per minute. And now we need to find our enthalpies. So to find H2, we were given the pressure and the temperature of the air. So for 295 Kelvin, we can turn to table A22, and at 295 Kelvin, right over here, we have an enthalpy of 295.17, and the unit here is kilojoules per kilogram. So after we fill that in, we have to subtract H1, and to find H1, it's really the same deal. You have air, and this time you're at 305 Kelvin, and at 305 Kelvin, right over here, we have 305.22 kilojoules per kilogram. And next to find H3, so at inlet 3, we have a quality of 0.2 and a pressure of 5 bar, and of course it's R134A. So because you have a quality between 0 and 1, we're going to be using the saturated table because we're in the saturated or the two-phase mixture region. And we'll simply go to 5 bar right over here, and we'll look at our enthalpy for both the liquid and the vapor of 5 bar. So we have 71.33 for the saturated liquid and 256.07 for the saturated vapor. And so to find where we're at between these two saturated liquid and saturated vapor enthalpies, what we're going to do is use the formula of H3 equals the HF, the saturated liquid specific enthalpy, plus our quality times the difference of Hg minus Hf. So now we have H3 equals HF was 71.33, and our quality was given to us as 0.2. And now strategically, they give us a column in this table here called HFG, and it basically does Hg minus Hf for us, which is going to be 184.74. 184.74. All of this is in BT or kilojoules per kilogram. And if you plug this into your calculator, you'll have the H3 equals 108.28 kilojoules per kilogram. Now next we need to subtract H4. So to find H4, we have, again, R134A, but this time we have the pressure and the temperature. So we have 5 bar and 20 degrees Celsius. So at 5 bar, our saturation temperature is actually 15.74 degrees. So we're higher than that because we're at 20 degrees, so we must be in the superheated region. So we turn to table A12, and here we have 5 bar on this table, and we have 20 degrees as well. And right over here, we can find our specific enthalpy, which is 260.34 kilojoules per kilogram. And now with that done, we have our mass flow rate of our air as well as all of our enthalpies. So we can plug it into our calculator, and when you do, you're going to have that the mass flow rate m dot r equals 3.78 kilograms per minute. And that's your answer to part A. So once again, in part B, what we're looking for is the rate of heat transfer between the air and the refrigerant. So I'll go ahead and draw that on the schematic. So remember that heat transfers from hot to cold, always. So therefore, in the case of this heat exchanger, it's going to be transferring from the air, the hot air or warmer air, into this cold refrigerant. And we're going to call this QR. Q dot R. So to find Q dot R, or the heat transfer into the refrigerant, what I'm going to do is I'm going to do the energy balance over just the refrigerant in this instance. So we're going to have 0 equals Q dot R minus W dot R plus, and then we're going to have a single inlet, single exit control volume in this instance, which is going to be M dot R, so times M dot R, and we're going to have H3 minus H4, which is inlet minus exit. And now we can cancel out that power because, again, this is not a power consumption device. And I'm going to rearrange this and find the heat transfer, which is going to be equal to the mass flow rate of the refrigerant times the difference in enthalpy. And we've already solved for all of these, so I'm going to set an equal sign, and for our mass flow rate, we have 3.78 kilograms per minute. And our enthalpy at 4 was solved above, and it was 260.34. We pulled that right out of the properties table, actually. And then H3, we did solve for H3, and that was 108.28 kilojoules per kilogram. Now, if you just plug this into your calculator, you'll have that Q dot R is going to equal 574.79, and the unit for this is going to be kilojoules per minute because the mass flow rate is kilograms per minute rather than kilograms per second. And because this is a positive number here, because it's not a negative number, you know that's in fact into the refrigerant. Had it been a negative number, this would be exiting the refrigerant.